Okay, let's get started. We managed to come to the final lecture. Your teaching staff is barely alive, so hopefully we make it through this lecture. I hope you all are feeling better. You know how I said this course won't really have this winding down phase. I'm gonna stick to my words. We are still going hard even this last day. But I really want you to know about LoRA because it is something you will use regularly when you use this model. So I think it's pretty important. And then I also want to tell you just a little bit about this course was all about how to use language models for NLP applications and understanding what language models the core piece of our solution is. And we have done that. I hope now you feel way more aware of what language models are and how to use them for NLP applications. But I also want to mention just briefly and quickly how people have done NLP before LLMs and what kind of things they were trying to do to be able to do applications like, let's say, sentiment classification. So yeah, we have lots to do today. Before we jump into the content, I'm gonna go over just a few logistics. We have a final exam, of course, and we are scheduled to have it on December 12th. So we have time until we have the exam. And the exam time is at 1 p.m. You will have 2 hours. The exam will be here, and it's going to follow basically how we did the midterm. There is not going to be anything quite different. Only the content will, of course, be different, and it's going to be everything that we have talked about after the fall break. So only that piece. I know I said I will bring your midterm notes, but I again forget. So if you want your midterm notes, shoot me a message. I honestly don't work a lot for my office, but I can swing by or give it to Nate as well to distribute if you want them. So sorry about that. I just keep forgetting. I promise I'll bring them here. But if you want them, I am happy to give them back to you. You don't really need them for the final because the final will be about completely other set of topics. One note that I want to highlight that's different. There are not going to be bonus questions for undergrads. I went a little bit too overboard with giving you all sorts of bonuses. So, you know, your scores are great, but a little bit inflated at this point. So there won't be any bonuses. And I recommend that it's probably good to see how much you, as an undergrad, prepped for the midterm and what your score would be if I haven't given you any bonus points. And that can kind of give you a sense of, all right, should I be maybe learning more if I want a certain grade, if a certain grade is what you want. Yeah, I didn't write here on the slide, but please don't be late. I won't be able to allow you to take the exam if you are late more than the first person that leaves the room. And likely or unlikely, I don't know, there are folks here who write these exams super fast. I would say maybe if you're late more than 15 minutes, it might be too late for you to take the exam. So come here on time. Okay, again, as in a midterm, you can have one page per side of notes, ideally produced by hand. If you write them electronically, just don't make those weird ones where font is minimal and no space whatsoever. The idea is not that you have like all the materials here at the exam, but rather if you're just feeling like you're starting to forget certain things, write them down. So it's like I think you are producing while you're learning, not a cheat code. Any questions about the exam that I haven't mentioned? Yeah.
Where will it be?
Oh, yeah, it is right. Yeah. Yeah, I will double check, but yeah, in the schedule, you know, they don't send me anything about this. I need to find it myself, and so I have the same resource you have, which is basically that link on the webpage. Yeah. Okay, and then I also sent an announcement about course feedback. Sorry, guys, just a second. Yeah, I would really appreciate if you would complete the course feedback. I mean, I keep changing things for better or worse in my courses, and I really do take the feedback seriously. And also it helps my review because these feedback of yours is then read by other professors who then report on my teaching, and that's all kind of put together for my tenure. Okay, so now today, as I said, we are going to finish LoRA and QLoRA, and then we are going to briefly learn about what is linguistic structure. So today's lecture is actually, it's funny because it's going to be a nice representation of how diverse NLP is. We are going to start with LoRA. Last Wednesday, we briefly started to talk about it, and we talked about matrix rank and matrix decomposition. So it's a little bit mathy. Then we know about, like from the last lecture, we talked about quantization, and we are still going to talk about this. So there's going to be like float precision, which is something we typically learn in our CS courses. And then we're going to end up with linguistics. And that's kind of what NLP is, all the mix of these various topics. And these days, more and more human-centered approaches. So a lot of HCI these days as well. Okay, so I'm going to quickly start because we have covered this at the end of the last lecture. But we have said that with quantization, we have, and KV cache, we have basically focused on how to speed up the inference. And then we have turned into the question of how can we speed up the fine-tuning of the models. And I said that there is a family of these algorithms for speeding up fine-tuning called parameter efficient fine-tuning, or PEFT, where instead of fine-tuning the full LLM, you are fine-tuning smaller number of parameters. And I showed this taxonomy just to present you that there are so many different ways people have suggested to go about this. The one approach that's stuck around and is quite often used is LoRA. So for understanding what LoRA is, we need to some building blocks. First of all, building block is what is the rank of a matrix. It's the maximum number of linearly independent rows or columns in the matrix. And I have told you that people have reported that weight matrices in the transformer architecture. Here, this citation is for the attention layers, but even the feed-forward layers, all of those weight matrices are low rank. Okay, we somewhere potentially, I have learned that this is actually not learning the algebra in the meantime, I check, but maybe you know or not, it doesn't matter. We are also for LoRA going to use rank decomposition, which is a factorization of a matrix, m by n, not necessarily square matrix, into product of two matrices whose shapes are determined by this rank R of the original matrix. So it's going to be a product of m by r and r by n matrices. And the key thing to remember here is that your original matrix, for example, here has 25 values, but its rank is really low. It's only 1. So when we do a product, a decomposition, a rank decomposition of this matrix, with these values in these two smaller matrices, vectors here, we are actually needing to record smaller number of numbers. So here we have only 10 numbers to kind of store to represent 25 values here. And that's a key property that we are going to get with LoRA. Okay, now this is an ugly looking slide, but bear with me. So let's focus on the visualization. So typically when you are running your normal transformer, you have a recurrent representation of a token, right? Some d-dimensional vector. That d-dimensional vector, as we know, is very often linearly projected. It's linearly projected in attention mechanism into query keys and values. It's later projected in feed-forward layers, right? So once we project it, which is a product of that token's representation with the weight matrix, we just get another representation, right? And when we are fine-tuning, we are changing the weights of these matrices. What QLoRA is going to do, it's going to first embrace this view of what the fine-tuned matrix looks like after fine-tuning. So after fine-tuning, you are going to get some new matrix with some new numbers. But you can always write it as, okay, it's a sum of the original matrix, let's call it W0, plus some delta, right, to get to that fine-tuned matrix. And they say, okay, let's keep then these pre-trained weights frozen, and let's try to learn the delta. And instead of trying to learn the delta of the size m by n, they are saying, let's try to rank decompose it and then learn the weights of matrices that are part of the decomposition. So here, those matrices are A and B. Initially, they are going to have values that we set for A to be random and for B to be set to 0. Set to 0 because later we are going to multiply B and A. And if we are starting from at a starting point of fine-tuning, we are starting with W0. So W0 plus B times A, when B equals 0, gives us W0, which is. Okay, so we start with those values for A and B, and then we are trying to learn during fine-tuning not the weights of the original matrix, W0. We are not trying to adjust them further, rather we are adjusting the weights of A and B. And once we are done with that, right, then we have our final matrix. The fine-tuned one is W0 plus delta W, but delta W is actually product of B and A because we are using the rank decomposition. So if we were using just original transformer, if this is X and this is the output of the linear projection, then we would multiply our token representation with the fine-tuned matrix, which is just written in this fancy CN4, right? There is nothing special about this. However, now that we have decomposed delta W into product of B and A, this projection turns into this one. Okay, there is just a single detail here. There is this scaling factor, alpha over R. Basically, you can think of alpha as how strongly do you want to change weights in B and A relative to the rank you have chosen. So higher the alpha is, larger the values in B and A are going to be. Okay, let me see. So key thing to remember here is that by this decomposition and rank being much slower than dimension of the model, you are in these matrices A and B storing less weights. And then if you need to change less weights, the fine-tuning process is simply going to be quicker because there is less to do. Let me tell you a little bit more about certain hyperparameters. Oh, yeah, go ahead.
In those previous equations, is H just the output of our inputs times the weights?
Yeah, so if this is input X, the output X times W is H.
Got it.
Yeah. Okay. All right, so just a little bit more on with these hyperparameters. First of all, there is this wonderful guide that I highly recommend checking, which overviews all sorts of hyperparameters for LoRA at the perfect level, I would say. But two things I want you to think about are which weights in transformer are we going to change. In original LoRa, they said, well, let's add these, by the way, these A and B are often also called adapters. They said, let's froze the entire transformer and add these adapters that we are going to fine tune only to matrices in attention that do the linear projection, so query key values, right? And they said that that seems enough for them to achieve good performance. So if we didn't need to put it, let's say, on feed-forward layers, why not? Like less of adapters we are adding and less parameters we are changing, everything's going to be faster. However, later, few LoRa that we're going to learn about in a second had shown that they actually need to fine-tune add adapters to all weight matrices in transformer. And as far as I know today, that's pretty common to add these adapters to every single weight matrix. So I would recommend just adding it there. It's maybe going to make things slightly slower, but you're for sure not going to be great in performance. And then the second obvious question is what is going to be the value for our rank R? And here, of course, the smaller they are is less values we need to store in A and B, and therefore we need to change less weights, and therefore everything is gonna be faster. So smaller R is quite appealing, right? But of course, if you are if the actual rank of the original matrix is much larger than something you have chosen for R, then your low rank approximation won't be good enough. So these days recommendation is to start with something like 8 or 16. This is going to give you a fast fine-tuning process. But if you start to get performance that doesn't seem right relative to the full fine-tune, then people recommend going up to 128. And then for that alpha hyperparameter, recommendation is either set it to rank, so scaling factor is actually 1, or setting it to 2 times the rank. Now, I want to just hone in to benefits of LoRa, because our starting point is to make the fine-tuning more efficient. So let's again go over why everything is more faster. The argument is everything is faster because we have less parameters that we are changing with matrices A and B than relative to the original weight matrix, right? So because there is less things to change, everything will just naturally be faster. However, one maybe potentially not so obvious consequence is that by using LoRa, we are going to significantly reduce VRAM, so GPU memory we need. One thing I have never mentioned, and it's really probably hidden everywhere until we start looking into it, is that your optimizer, when you use it in PyTorch, it is going to, especially if you use Adam, which uses the momentum as well, it's going to record all of the gradients and all of the gradient variances and the bias corrected versions and whatnot for all parameters. So your optimizer is carrying a lot of memory itself. So now, because you have less parameters, you need to remember the gradient, the variance, and whatnot of, then you need simply less memory to record all of the necessary information. And indeed, LoRa reduces the VRAM usage by up to 2/3. So it's a huge reduction in the VRAM. And now, remember, everything is connected. So if I can make use of more GPU memory, I can then place a larger model, I can train it, and I can get usually better performance, not necessarily always. So if you have more VRAM, if you were not able to place your model on the GPU memory before, all you had is to train it on CPU, which takes a very long time. And now, because you have more VRAM, you actually have a chance to train with GPUs, which additionally speeds up the time, right? So it speeds up training in two ways. Okay, so now let's talk about LoRa. Before I go ahead, let me see whether it is clear how LoRa works. Like we start from we take some pre-trained model. This pre-trained model has a bunch of weight matrices. We select some we are going to fine tune. Let's say we chose all of them. For every single one of them, we are going to initialize matrices B and A. B is going to be just normally distributed. A is going to be initially all the zeros. And then we are going to change the weights of B and A, keep the original weights frozen. Then when we are done with fine tuning, we are going to pass our token representation through both W0 and through B and A, B times A. And we are going to get two vectors that we are going to add together to get the representation. Yeah.
What sort of performance impacts are typically seen when applying LoRa? Comparing a model that's been fine-tuned with LoRa versus not.
These days, almost none. Yeah. So today it's something we just use. It's pretty common. Yeah. Interesting. Especially also with QLoRa. LoRa with 4-bit in itself wouldn't work. Oh, sorry. LoRa Okay, I'm jumping ahead, so this might confuse you, but let me hold off on this comment when I get to. Yeah.
Was it random or initially? Or random or normally?
Yeah,
Okay.
it's the same to me, randomly flown normal distribution. Okay, pretty simple, although the slide suggests something scarier, right? So now, we would like to push this even further. So we have learned about the quantization, right? And we know that if we have a quantized version of a model, especially if it's 4-bit. Remember that table I have shown you where like the gigabytes of GPU memory you need like drastically reduced when it goes from 32 float to 4-bit precision. So that kind of might make you think, okay, well, can we use a quantized model, and then instead of starting from LoRA from those pre-trained frozen weights that are in full precision, can we start with a 4-bit one? And LoRA will do exactly that with a bunch of additional tweaks to actually not degrade the performance. So LoRA is an extension of a LoRA, where our pre-trained weights that we keep frozen are going to be stored in a 4-bit precision instead of full precision or half precision. However, we're going to need to use smarter representation for this 4-bit. So the first addition that the authors of LoRA have introduced is a normal float, a new kind of precision. And it was motivated by the fact that our weights are normally distributed because we use layer normalization. We make them normally distributed around 0, right? But then when we quantize, right, like we are choosing those bins, we are not, all the bins get equal chance of getting numbers, right? And here they want to basically tweak the quantization, and I won't show you the formulas, that level of detail is not necessary, but they also want that the number in the quantized scale also follow normal distribution. So they do some tricks. You remember those 4 equations we have seen with quantization? We add some tricks to those equations, change them slightly such that what the quantized values we get, discrete values from our normal from our continuous ones, follow also normal distribution. So that's one change, and this is called normal float. The second change is what we have actually talked about. You will need to quantize the quantization scaling factors. Remember when we said that the issue with quantization are outliers. If you have some huge outlier and you're basically trying to, as the visualization showed, the one we have seen last week, as you're scaling from your continuous values into your discrete, if you have one that's complete outlier, but everything is determined by the range of continuous values, then everything is going to be messy and too many values that if we didn't have that outlier would actually be spread across the quantized range are going to be kind of merged together. So I mentioned we are using group quantization, right? Like instead of taking the min and max value of the entire tensor, we said, well, let's try to do it row-wise or column-wise. And even within a row or a column, we can quantize in smaller ranges, right? And that all sounds great, except that now every single one of these, groups that we are quantizing individually has a scaling factor. And if we do this for many weight matrices that we have, now we have a lot of scaling factors to record as well, and they take memory. So what we said we can do is quantize the scaling factors themselves as well. And then the last one is not related to flow precision or to quantization. Rather, it is related to this optimizer. So, as I said, optimizer itself needs a lot of memory, right? And this can become a huge issue when you are processing long inputs because long inputs are associated with memory spikes in GPU. So what LoRA folks have said, well, let's try to kind of orchestrate this GPU, CPU memory a little bit for these cases. If we are noticing this memory spike, let's put our optimizer state, including all of those gradients and whatnot, onto CPU. Let's process this current input that needs so much memory. Once we have processed it, let's release like computation we needed for processing and put the optimizer back onto the chip. So there is a little bit of shifting around things from CPU on GPU. Okay, so this all together brings me to QLoRa. So QLoRa is an enhanced LoRa. So we are still doing that with, adapters that represent rank the composition and all of that. But instead of starting from our pre-trained transformer in its whatever precision it's given to us, let's say float 32, we are going to record it and store it onto memory in a 4-bit normal float. Then we are going to, because we are going to, for this 4-bit quantization, have a lot of these scaling factors. We are going to quantize them as well. I think in QLoRa, they use 8-bit to quantize the scaling factors. We are going to use our LoRa adapters, which are those matrices B and A, and they themselves are going to be stored in higher precision in BF16. And those serve to reparameterize that delta, right? That we are going to add to the frozen weights later on. And we are also going to use the page optimizers. So all of this together is QLoRa. So let's also go into how then projection age. So if we have a token representation X and we linearly project it with the W here represents like a fine-tuned matrix. Oh no, sorry, W here, I should have written W0. This is let me do it right away before we confuse each other. Okay, so this is okay. All right, so okay, so we are we don't really have delta W, right? We have these matrices B and A. So how can we mimic doing this computation with our adapters B and A? So first thing you're going to do is remember that we are quantizing everything, but when we actually need these things to do computation, we dequantize them into this and use part of GPU hardware that serves for on-fly computations. So we first quantize the quantized scaling factors into 32-bit floats. Now we have our scaling factors in nice precision. Now we use them to dequantize our pre-trained frozen weight matrix, again into full precision. Then we calculate B times A. B and A are in BF16. And whatever we get out of that product, we add to the frozen weight matrix that's in full precision. Now we can calculate the product of our token representation X with this addition of two matrices. And now we have its representation. And then once we are done, we can remove all this dequantized version and free the memory, right? We don't need them anymore. Okay, any questions?
So what are the scaling factors exactly?
We have covered that in the last lecture on quantization. So if that's unfamiliar, please check that lecture. You needed to do this quantization that I'm talking about. Did you have questions? Yeah.
No.
Maybe. you might have mentioned this the last time, so right now we're doing quantization potentially over rows or columns,
Yeah,
but could we quantize essentially like bids of percentiles if we have like weight matrices, right? You could imagine, okay, maybe I take 3 sigma outliers and I can quantize all of those together, everything between 2 and 3, etc., or
Yeah.
something.
I think the Hugging Face way of doing things will be to just keep the outliers in full precision and forget about it. Just leave them there and then you quantize everything else. Yeah. But then even then, you know, like it becomes like now you have got rid of these outliers and now these become outliers. So you still want this block group quantization to handle all of those additional cases. Yeah.
Okay.
And it's always for, as I said, for 4-bit precision, which is really low precision, right? You need these extra steps and double quantization and all of that. Because I mean, by double quantization, I mean we have done group quantization. With 8 bits, you don't need, I mean, who knows what you need, right? But with 8 bits, it's higher precision relative to 4-bit. And then you don't necessarily need to do group quantization, and then you don't need double quantization as well, because you don't have so many scales. Yeah. Okay, so I think one thing that might be in your mind now is like, I will never do this. This is so much work, right? So who is going to implement all of this? And as always, Hugging Face has everything covered for us. But I do want to, this is one thing, how to use LoRA for fine tuning, that there are bits and pieces out there in Hugging Face documentation, but it's not super clear. So I just want to give you some screenshots from some of our code for how to do that. So first of all, from transformers, you have bits and bytes config, and there is itself a library bits and bytes that we use for using LLMs with k-bit quantization. And then there is also another library called PEFT, which is a library for using PEFT methods like LoRA. So already suggesting that there is a lot out there, lots is implemented. So you will need to create this bits and bytes config. And here you are specifying that, yes, you want to load the model in 4-bit. The type, data type you're going to use for your model. Here you see how we place this NF4, which is this new representation, introduced in QLoRa. And then here, this is something that it's probably not immediately clear what this is for. But remember that there is things we store on GPU memories, and then there is things we use for computation, the current computation of GPU. And those two can be different data types. So you have seen how in previous slides, I have said here that we are going to actually dequantize and do things in higher precision. This is where you specify what the precision for dequantized values is going to be. Previously I think I said full precision, but maybe half precision is enough. And then whether you're going to use double quantization or not, you are also specifying that. So this configuration basically represents everything I have shown you previously for QLoRa. Okay, then you're going to need something called LoRa config. Here you are specifying hyperparameters of LoRa, such as RAM, alpha, which modules you are going to add the adapters to. There is also LoRa dropout, that's just adding dropout to these weights. We typically don't use BIOS, and for example, here you will need to also specify what kind of task this is for. So a causal element means language modeling. Okay, so now you need to load your model. Typically in Hugging Face, we load the model using from pre-train together with appropriate auto class. So here auto model for causal LM, and then from pre-train. If you were doing just a standard full fine tuning without these adapters, you would have everything except this line here. So here you are saying, all right, I'm doing quantization and of this model, and I'm going to use that set of here parameters that I defined over here, right? So this tells to Hugging Face load this model, but also load it in 4-bit normalized float and everything else. Okay, so here there is also another thing. This is maybe a little overkill, but I'm going to mention it nevertheless. You might want to use use gradient for checkpoint. It's pretty not advanced. I mean, you all would understand it, but this is not the course or time for teaching you about it. But basically, one thing that folks can notice is as you are making these activations themselves start to use too much VRAM. And you need all these activations because when you do back propagation, remember, due to the chain rule, you need all of these activations in the backward pass. But then maybe you can't even do the full forward pass because you have stored all these activations to do the backward pass. So what this does is basically every few steps, it drops the activations. It removes it from the VRAM and you recompute it during the backward pass. Of course, this is going to be slower because now doing the backward pass, you are doing forward passes to get these activations. But it does help to actually be able to do a forward and backward pass using GPU. So if you use gradient checkpointing, then that's what's going to happen. It's going to be slightly slower, but if this is the only way you can actually use GPU, using GPU will always be much faster than on CPU. So trade-off might be worth it. Okay, and this last bit gives us a get path model. Let me see from which library. Okay, I was taking this screenshot, so it comes from probably PEFT library, although here it's dropped. And here, basically, you are going to now you have your pre-trained frozen model. Here is where you are using some implementation from the library. These matrices, adapters A and B, and recording them with hyperparameters you chosen for LoRA, which are stored in LoRA configs. So here you have all those hyperparameters. That means using these hyperparameters, here we would create appropriately shaped B and A, initialize them how we wanted, and all of that. Okay, and now basically the last 2 bits are more or less how you would prepare your code for full fine-tuning anyway. So you always have these training arguments. And the only thing that's new here is that here optimizer is paged Adam 32-bit, which since we have just learned about paged optimizers, suggests we are going to use Adam with those, navigation of CPUs and GPUs. And then the trainer is exactly the same as you would use it for full fine-tuning. There is nothing new here. And then you do trainer.train, and this is how you fine-tune a model, right? So to use QLoRa, you kind of rely on Hugging Face. You do mostly what you would do anyway. If you have, to this point, not checked any of those Hugging Faces notebooks, I really highly recommend you do. Again, there is nothing there to do but just go over it yourself. So I think that's definitely worth your time. So the only difference is that you prepare all of these config files, and that's super nice. And once you do that, you can use QLoRa and actually train much larger models onto the available GPUs. Okay, are there questions about QLoRa? Yeah.
What reason would you use regular LoRa over QLoRa? Or is there any reason to use LoRa now that QLoRa is the thing?
That's a good question. So in my research group, very often we want to use the largest possible model we can. And that means we are going to use QLoRa, right? Because if you're pushing the size of the model, then you need all these tricks and things to actually fit it on the available GPUs. So one, like you would always use QLoRa if your goal is to try to fine tune the largest possible model, because most likely you just won't have enough GPUs on disposal. Or remember, even if you do, like CHPC is actually well resourced, getting 8 H200s is gonna be, you will be in a queue and you might wait for a very long time. So even though the resource is there, just getting it might be really challenging. So that's when you're using QLoRa. Now, if you're in a situation where you have option to run full model and LoRa and QLoRa, I think it might be even worth to try all three of them. And if you get same performance, then that means, oh, I can use QLoRa here without losing any performance, and I can try many different runs of the things. Because usually we don't run just one training run, like we run hundreds of training runs, right? So if you see, well, I can use the fastest method to get the same performance, then it's allowed you to experiment more. So you would go with that. Yeah. And as I said, these days we kind of assume that the performance won't drop with any of these notably. I haven't seen it, but if you have, resources to double check, why not, right? Like,
Okay.
to be sure. Yeah. Okay, so let me go over this little grid diagram that I have created to kind of wrap the story about efficiency, right? So there are two kinds of efficiency we were talking about. One is inference efficiency. Your model is trained, or someone trained a model, you're just prompting it, you're just trying to get test time outputs, right? And there is fine-tuning efficiency. For inference efficiency, we were talking about how can we speed up the computation for very long sequences, right? Like long sequences naturally will require more and more and more and more processing. So if we have a very large, I don't know, contract based on which we want to do something, just processing that entire contract might take a long time, and we want to do that faster. And then we talked about KV cache, right? Like we said, we can do our attention mechanism at the inference time, the way we do it, just a little bit smarter, right? Like we discuss which computations are being reused in the next decoding step. So instead of recomputing them, we store them and use them. Then we also talk about, okay, how can we reduce the memory usage? Because more GPU memory, we have more things we can do, right? Either we can speed up a single instance computation, or we can serve multiple people at the same time, because every person would be done one instance in a batch. So that brought us to quantization, which is basically presenting our model from its full or half precision into something like 4-bit precision, like we talked today. And then we moved into the fine-tuning efficiency, and we have said, hey, if we just have less trainable parameters, things are going to be faster to train because there is less to do. And we have also said that we can speed up fine-tuning by reducing memory. This is it requires a little bit of mental gymnastics. You just need to embrace that. All right, hitting CUDA memory errors happens all the time. That's the main error we are going to get when we use this model. So, and then if you run into that error, you can't use GPU, and then attempting to train anything on CPU, like it depends how small your model is, but generally we don't do that. So you kind of need to find a way to actually be able to use your model onto the GPU, and then as soon as you can, you reap the benefits because everything is faster on the GPU. And today we have talked about two ways to go about this. There are basically one main approach and two flavors of it. LoRA, decomposing that delta that brings us from pre-train weights into fine-tune weights with rank decomposition when the rank is really small, as I said, 8 or 16, where representations themselves today are at least 4,000, so quite a difference, right? And then QLoRA had just like brought the LoRA to the whole other level by using 4-bit quantization. Okay, So that's as much as I want to say about LLM efficiency and wrap that part and move on to whole other topics. So are there any questions? I feel like I'm doing pretty good on time, so feel free to ask. Okay. Yeah.
This is about like different, past lecture. Could you explain the expectation again in the equation?
Oh, yeah, I would not like to go into our ledger, but we can talk after. Happy to answer that question. Yeah, that's just a whole our ledger is a different topic.
Is this, will we next learn about structure prediction?
Okay, so I made this little diagram to kind of recap how we approach building NLP solutions in this course, right? So remember, I mean, I don't know whether you remember, but in the very first lecture, I told you tried to explain what NLP is, and I said, right, one of two major goals in NLP is to build computer programs that can kind of understand language and help us with, language-related activities. And we said that one computer program that we are going to embrace in this course are large language models. And we are going to learn what they are and then how we can use them for a bunch of different applications. And we did that exactly that, right? Like you have learned that what LLMs are. We have quite extensive build-up, like with background to the LLMs. And then we have talked about those three major stages of LLM development: pre-training, SFT or supervised fine-tuning, instruction fine-tuning, and then RLHF, reinforcement learning from human feedback, which today is done with, as we learned, with DPO without RL, but still alignment. We can also refer to that stage as alignment. So you have a very good mental model of what LLMs are. And you also know that you have options between prompting the model. So that means just not changing the weights, and fine-tuning the model where you have labeled data and you can change the weight to make a model that's specialized for your task. And applications we have covered are things like machine translation, where we have some text in some source language, and then we try to translate it in another language. And don't forget about evaluations. That's really important, right? Like we have talked about a lot of text generation evaluation, from human evaluation, Blue, BERT score, Rouge, LLM as a judge. Don't forget about all of those. Evaluation is very, very important. We talked about summarization, classification, retrieval, reading comprehension, all of that. But all of that was kind of, we crafted our inputs, we placed them into an LLM, and then depending on whether we use the classification head or language modeling head, we had either produced a text or predicted a label, right? And this is kind of how you now know how to build NLP applications, and they are certainly going to be, if you end up being hired to do NLP stuff in a company or you do research, these are certainly approach you will gonna use. However, before LLMs, and this is, before even when I started to do NLP, I myself have immediately started with neural networks. So let's say 10 years back, how NLP was done, it was by producing a so-called linguistic structure. So you would, as always, tokenize your text, but then you didn't have this nice token representation that we are building with Transformer that implicitly capture all sorts of necessary phenomena. And we know that they capture necessary phenomena because they are capable of doing things like summarization. So it must be the case that there's something useful is encoded in those representations. Previously, people had to define what are useful language features, and they needed to present it to the model. And those useful features are those that are under this realm of linguistic structure prediction. So today, I want to go over these some of these parts of this structure that have been very important for these approaches. And the reason why I do want to talk about this, although it's the last lecture and you obviously are all, I have invested so much resource for you to learn LLMs, is because this still serves as a great meta language when we are developing NLP applications. So for example, if I'm evaluating my language model, I might do some kind of error analysis where I check for which kinds of text my LLM fits. And I might notice, from 510 instances, it seems to be failing for words, let's say. And then it's useful for me to know that there exists part of speech tagger and that I can annotate my words in my documents with grammatical rule. And I can find all the words in a large collection of text automatically. And then I can check automatically with a large scale analysis whether my model fails for a large collection of verbs or not. So although I don't personally find these outputs of these structure prediction model necessary for a lot of applications, they are super useful meta language when we discuss what might be going wrong with our application and other things that I'm going to mention later, but just wanted to give you one explanation. Okay, so as you see from this little diagram, we will have tagger, parser, NER, and a few more. So let's just talk about what the tagger, parser, NER are. Okay, so first thing is part of speech. Part of speech are categories of words based on their grammatical relationship with neighboring words. Here you see a list of part of speech tag that comes from the Pentrim Bank. And you can see some familiar terms like verb, base form, right? And you will see noun, for example, here, right? So some of these grammatical roles you have certainly seen before. Then there is a task of part of speech tagging, where you are given a tokenized sequence of words, and you need to predict the part of speech tag of each one of these words. And this is an example of a kind of a task we call in NLP sequence label or sequence tag, where each word in the input or each token in the input gets the tag. Okay, so here we have Jenna will back the bill. We have each one of these words gets labeled, which is different from sentiment classification, where entire sequence gets the label. And these days, even our BERT-like model will be used for part of speech tagging, where ignore that we are working with subword tokenization. There is a way to handle that, just a little hack, nothing special. So let's discuss this as our tokens are actual words. So you pass your inputs through BERT, and then you can have a classification head at top of every token's representation. It's going to have the same classification head, not a token specific ones. And then you make a prediction. So here is an example. I will book a room at the hotel. To each one of these words, I will book and so on. You give a label. And this example also serves to show that there is ambiguity. So here we have book as a verb in the first sentence, and then book as a noun in the second sentence. So you can't just have a lexicon of words and say this is your part of speech tag. Okay, so why did people use part of speech tags to build these solutions to NLP tasks? Part of speech tag, knowing what the grammatical rule of a word in a text is going to be useful for our next task, which is called syntactic parsing, and we are going to come to it in a second. But then for applications like machine translation, it is useful to know what the part of speech of words are. So, for example, here I will read the example. In Spanish, adjectives come after the nouns. in English, they precede the nouns. So if you were doing machine translation, not with neural machine translation that kind of implicitly handles all these things, but rather you are building a system where you need to say what's important, then you might say, well, notice that in source text, the adjective is after the noun, because I'm translating to English, make sure that the adjective comes before the noun. Then, for example, for sentiment, you know, we express our sentiment with adjectives and adverbs a lot of times. So you might want to find those and then work and do something extra with them, and so on. There's a related field on computational social science and digital humanities who are working with large scale corpora, collections of text, and for them, it's useful to apply these kinds of tools to just study whatever they want to study. So maybe, for example, here I have an example. Maybe someone wants to study linguistic change, like creation of new words or meaning shift, knowing, you know, checking, okay, there is this word, it appears 200 years ago and appears today in these collections of text. How did anything happen to this word? Had it changed? And maybe they notice suddenly I'm seeing that this word that had part of speech tag to be adjective in 200 years ago today has now. I'm making things up. I don't know whether there is an example like this, but this is kinds of things they're interested in. So there is this tool, they're using them to apply them to large collections of texts. Okay, as an example of this cultural analytics and how we use part of speech for that, I recommend checking out this article. But let's move on. So next part of the pipeline, the classical NLP pipeline, is our named entities. So named entities can be anything that can be referred to a proper name. And most common tags like that are person, location, organization, and geopolitical entity. But this term named entity has been extended in NLP to mean many other things. So for example, in some specialized domain, so maybe like in biology, you might define named entity tag set that fits your purposes. So instead of having person tag, you might have gene, protein, disease, and stuff like that. One challenge with named entities is that they are often multi-word phrases. So, for example, Boulder, Colorado, in my geopolitical entity example. And unlike part of speech tags where one word gets one tag, now multiple words are associated with some tag. And this becomes challenging, like where does this named entity start and end in text? And I will tell you how to do that. It's important to know that. So named entity recognition is another example, like part of speech tagging, of a task that's very commonly approached as sequence labeling, where you have a sequence of tokenized words and you have a set of entity types, right? As I had previously had, you know, on the right, there was a list of part of speech tags, where those are possibilities in which I can classify a given word. Also with named entity, I need to have a set of possible entities, right? Like, let's say it's only 4 entities: person, organization, location, and geopolitical entity. Okay, so now we want to assign so-called BIOS tags. And this serves for this segmentation problem. So here we have a sentence, and you can see how some entity like United Airlines Holding is spanning 3 words. So to kind of indicate that this is a beginning and this is the end of the entity, we are going to use this schema where every entity will be extended into a few possible labels. Let's pick on BIO, which is the most commonly used. So if I had named entity person, I will create 3 classes, B-per person, I-person, and that's it. Outside is used for all of them. So you are kind of expanding your possibility of your classes. So here you would start with, this is the beginning of organization, this is inside, and then let me place outside, and that means that this is the ending word of the previous named entity. So whenever you have some input text, and you are using this approach where you are classifying each input token into one of the classes, but then you have a problem of multi-word phrases, you're going to use typically BIO notation, okay? So again, why has this been a task in NLP? Well, for example, if we had targeted sentiment classification where we're not just interested what is the overall sentiment of a word, but we are interested in what does this person think about this thing, this product, right? Like what is the sentiment about a specific product, not about everything that's said. Or in a movie review, there might be, what is their attitude toward this actor, right? Like they might not be overall happy with people, but they might praise someone actor. So having a named entity and finding a person, we can kind of help the model realize, well, when there is a person and something else, some other feature that's kind of associated with a certain sentiment label. Then question answering questions about an entity, extracting facts about entities and so on. And again, these days, a lot of this cultural analytics stuff. So for example, here it says that you may want to study how British novels depicted India during the colonial period. And you have all these novels. It's a lot of text. You certainly don't want to read them all. You might use NER to find all the locations, all the people, all the dates, all the venues, and then use some other techniques to kind of put everything together to understand what's going on. Another pointer to how to use NER in spacing for these kinds of cultural analytic stuff is here. Okay, so now we have a piece of text. For this piece of text, we have part of speech text. So let me say we have token 1, token 2, token 3, token 4, and so on. We have, I don't know, noun, verb. Those are part of speech tags. Maybe we have here beginning person, outside, beginning organization, inside organization, and things like that. So you can, if you're thinking about this in Pythonic way, you can imagine, okay, I have a tokenized list, and then for every one of these lists, I also have another list with information about type of speech tags and the named entities. Okay, so you see how we are building that structure, right? This is what we mean by that linguistic structure. And now you would also do on top of this something called syntactic parse, right? So let me go over a few definitions. First, syntax is the set of principles under which sequences of words are judged to be grammatically acceptable. We have just learned about one of the most basic syntactic concepts, which is the syntactic role of a word. So that was part of speech tag. And we are going to now think about word and phrase order, right? So not only, okay, this is a noun, but oh, this noun had appeared before this word and things like that. Grammar, informally, is the broader term that encompasses implicit rules by which speakers intuitively judge which strings are well formed and what they mean. And grammar actually includes syntax and morphology and other aspects like semantics. And it's different from grammar formalism, which provides a set of mathematical rules and algorithms that can be used to generate this syntactic structure of language. And then all of this brings me to syntactic parsing, which is the task of assigning so-called syntactic structure to a sequence of text. And there are different theories of grammar, and the different theories poses different formalizing for how we should describe this syntactic structure of the sentences. The most common one are the constituency grammars and dependency grammars. And therefore we have constituency parsing and dependency parsing. Again, why did people use this? Why do we care? Like, how can this be helpful for building NLP applications? So knowing what is the syntactic structure can help these computer programs that are trying to understand human language get the right interpretation of words. So here, maybe this is timely after Thanksgiving, we have visiting relatives can be annoying, or visiting relatives can be annoying, right? And depending on what you want to say, this has completely different meaning. And this is also kind of a gateway to thinking about who did what to whom, which is for a while, and this is, I think, really hard to embrace now that you have ChatGPT, but question answering was really hard, right? So if you had a question, who chased the dog or what chased the dog, then knowing about what is connected with the verb chasing here, and that the subject is cat, the object is dog, can be helpful. And other applications, even the machine translation. So I think while back we really talked about multilingual pre-training data, we talked about how different languages have different word orders. So while English is very often subject, verb, object, some other languages are not. And then knowing the using the information about syntactic structure can help deal with translations better, and so on. I hope this is convincing enough that parsing and syntactic structure could be helpful. Okay, I said that constituency parsing will have, that there are two main formalism, constituency and dependency. Constituency parsing builds on the constituency constituency formalism. And this type of parsing is going to break a sentence in its constituent parts, where constituents are words or groups of words that function as a single unit within a hierarchical structure. So let me see whether we have any noun phrase. We do. So here, building is a noun, the is the determiner, the building is a noun phrase. Okay, so this noun phrase, it's a type of a group of words that can together function as this syntactic group. And very often the constituents parse trees will be represented. First of all, constituents are going to be represented in parse tree, and this parse tree will have this branching structure. So very often they'll look like the one on the slide. And constituency do make a lot of sense for languages where you don't have somewhat of the free word order, right? Or languages where the words, dependency of the words can be verified from each other. So for example, in German, you have this like split verbs where you split a verb in two parts. One part always appears as the second word in a sentence, and the second part of the word appears as the last word of the sentence. So now it's, like the constituent would be everything in between, and that's too large to include and wouldn't make any sense. Another spacey, what Hugging Face is for LLMs, spacey is for this classical NLP pipeline. So if you would like to use, you need a part of speech tagger, NER, constituency parsing, you go to spacing. However, as I just said, constituency parse tree are not great for all languages. And there you might actually benefit from dependency formalism, where instead of, basing it on constituents and phrase structure rules, dependency formalism is described solely in terms of direct binary grammatical relations between the words, and they are directed. So here we have a cat, and the cat has this directed arrow towards the, and the relation described between two of them is determiner. So this says The is the determiner of the word cat. And for dependency parsing, if you end up using it, most likely you will use the UD schema of universal dependencies, which is project that try to kind of make this dependency formalism unified across many languages, so across more than 100 languages. So the general philosophy is to provide a universal inventory of categories and guideline to facilitate consistent annotations across many languages. And then, that could, if you have dependency parsing in one language and dependency parsing in another, and you use same, schema to do dependency annotation, maybe doing some kind of cross-language application becomes easier, right? Okay, but I won't teach you about how to do constituency or dependency parsing, and most likely you will just end up using spaCy or another tool. Okay, so I want to wrap with two more. Everything I said about this linguistic structure so far was related to syntax, more or less. But way back when we were talking about subword tokenization, we were also talking about morphology, right? Like where we said that we inflect the word, so we can add a prefix or suffix, and then this changes the word. We have talked about word embeddings and a lexical meaning of a word. So when you are talking about meaning of a single word, that refers to lexical semantics. Now we talked about things like that are related to syntax. And now I just want to mention a little bit more, just briefly, obviously, about semantics and discourse. So semantics is the study of linguistic meanings. It examines what meaning is, how words get their meaning, and how the meaning of a complex expression depends on its parts. And unlike syntax, for which I told you just now, that we have constituency, dependency, formalisms, and based on these formalisms, we have built either the dependency or constituency parse tree. Syntax, has no standard format. There is no universally accepted structure for representing semantics. Although there are some attempts like, let's say, AMR or QA-SRL, where you represent semantics with a sequence of questions and answers. But one very commonly used in NLP before LLMs representation of semantics was through semantic rows. So in our text, we have some kind of events. They're very often represented with verbs, expressed with verbs, such as the event of seeing here, right, which is expressed with the verb so. And in this text, then you can, based on that event, try to see what are these semantic roles, which are basically other entities that are involved with this event. So here, the word John, it's the entity that is performing the seeing action. And Mary eat the apple, what is being seen, right? Like what is going on. So semantic role labeling has been one of these classic NLP tasks where given a sentence and some verb in that sentence, we were trying to find all the spans in that sentence, which represents the arguments for that particular event, such as who is doing this action, what is, how is this action done, what is being seen, and things like that. So again, this has been approached as a sequence labeling task where given a verb and given a semantic role labeling schema, very often prop bank schema, we would adding labels to the tokens using the same BIO notation as we did for NER. And then finally, discourse. So a discourse model is a mental model that understand or builds incrementally where interpreting a text, right? Like as you're reading a book and there are a bunch of characters and things, you are kind of visualizing these characters, and as something is happening to them, you're imagining them in these situations. And if something changes in their life, like now, book went 10 years forward, you imagine them being older and things like that. This is a discourse model. And in NLP, we use word discourse to refer to a coherent structure or group of sentences that make up the language, right? So coherence is one of the very often talked about aspects of discourse in NLP. So whether your text is coherent, whether they make sense together rather than just random assemblings of sentences. And one task in particular is really relevant, has been very relevant in NLP relating to discourse, which is knowing, like you have all these mentions of things in text, knowing which mention is referring to which entity. So for example, here, some made up text, Taylor and Morgan went to a conference in Seattle. Taylor was excited to unveil her research, while Morgan was keen on discussing her innovations in renewable energy and so on. As these sites go, every mention of Taylor, Morgan, her, or anything else, biologists, you want to kind of keep track that they are referring to the same entity. And this is called coreference resolution. So some terminology. First, mentions are linguistic expressions like her, Taylor, Morgan, they, and so on. Then we have referent. This is the entity that is referred to. So in here we are having three entities, Taylor, Morgan, or them as a unit. And we say that two or more referring expressions that are used to refer to the same discourse entities are co-referring. So mentions of Taylor and her are co-referring to because they refer to the same entity Taylor, Morgan and her to Morgan, Taylor and Morgan, and mention just they also refer to the same entity. And coreference resolution is basically the task of automatically producing clusters like these, where you have all these mentions in text and you are grouping them into clusters where each cluster refers to the same entity. So this means that your first needs to automatically find what the mentions are in text, and then you group them into clusters. Okay, I didn't have a slide for it, but there is one additional related task, and that's entity linking. So you can imagine having a knowledge base where, for example, we built a knowledge base out of Wikipedia, where every node in your knowledge base is now referring to some particular article in Wikipedia. And if you had text about real-world entities, then you can build these clusters, but you can also connect them to appropriate place in the knowledge base. And this is called entity linking. Okay, so now, why don't we do this? Like why, why don't we label our text with part of speech tags, named entities, saying which named entity refers to which one, and so on? And the reason is that our pre-training of our language models, we never told it to, we just said predict the next one. That's what we optimize for. But it turns out to know what the next token could be, the model had to implicitly learn all of these useful features, such as part of speech tagging, name, entity recognition, and so on. So there's this paper that says BERT rediscovers the classical NLP pipeline. What they did here is they use this interpretability technique where you poke into these representations to see whether they are active for, part of speech tag, named entity, and so on. And they have seen that they are. I have once given a lecture on these interpretability techniques. It's linked here if you want to know more. But the point is that we don't typically do this kind of linguistic structure prediction explicitly because we don't need to. It's seemingly already there in these representations of the model. Okay, I said already a little bit about this, but I still think despite us not using these, structural prediction explicitly very often for highly to moderate resource languages anymore, you might be using them for much low resource languages for which LLMs just can't do anything. Of course, but also I think it's just a very useful meta language, right? It's so much easier as us to communicate. If you tell me, oh, I have looked into this identity instead of trying to redefine an identity back to me. Okay, I'm gonna stop here. Before we all go, I just want to say 2 words. I really, really enjoyed teaching you guys. This has been such a great semester for me. Last year's semester was the worst semester possible, which was ended up with me working from home for 2 months for my safety. So just coming, I didn't teach then in spring, and I came back, and you all were really interested and engaged, but also very mature and calm. And I really, really appreciated that. I really needed that re-energizing myself for teaching after everything. So I really, really want to thank you so much for these couple last months. It was a pleasure to teach. Okay, thank you.